Right, so the final talk for the session, Steve will talk about dealing with the product constraints.
So good morning, everyone. So I'm Steve Malalel, and I'm going to present you the work that we have done with Victor Jung, Jean-Charles Regin, and Marie Pelleau about the product constraints. So to begin, why are we interested in these constraints? Well, real problems often involve uncertain events. For example, we cannot predict exactly the traffic on the road, and it's the same for the river. So we can decide to ignore these uncertain events, or we can take them into account during the modelization of our problems. And doing this adds a need for robust solution. That is to say, solution that satisfy a problem almost all the time, so solution that has a high probability to satisfy the problem. And then the product constraint can help to answer that the probability of an assignment of n variable is above some threshold W. And also we want to define this constraint with multivariate decision diagram. So why? Well, so we spoke a little about that yesterday, but an MDD is a complex data structure that represents a set of solutions. And so as for set, there exist operations such as intersection or unions between MDD. And we saw yesterday that solving a problem with several constraints is also similar to create the corresponding MDDs of these constraints and then intersect them. And there exists already many MDD for constraints, like for the all different, the GCC, the sequence, etc. So to begin, I will remind you what is exactly multivariate decision diagram to be self-sufficient, even if yesterday we already spoke about that. Then I will present you some construction methods for the MDD of the product constraints. After that, we'll see the iterative precision refinement, that is a kind of upgrade for the construction methods. And then I will conclude. So the MDD. So I remind you that MDD is a directed acyclic graph that used to represent some multivariate functions. So that is to say that indicates if a combination of n values is true or false, is acceptable or not. So for example, you have the MDD of the constraint are different on free variable, with here each layer represents a variable, each arc represents an affectation, and each path going from the root node to the true terminal node represents a valid solution. So here in red, we have a solution where x1 is set to B, x2 is set to A, and x3 is set to C. But now I will more focus on the construction of an MDD. It will help you to more understand the method that I will present for the product constraint after. So we build an MDD from the top to the bottom, so from the root to the true terminal node. And during the construction, each node holds a state, so it can be a number, an array of number, a set, etc. There is a kind of transition function that will indicate how we create the next node. And an important part for the compression is that if two different nodes get the same state, then we merge them. So I will show you a quick example with the MDD of the sum constraint, because the sum constraint and the product constraint are quite similar on some point for the construction. So the MDD for three variables, x1, x2, and x3, that are subject to their sum must be greater or equal to 5. And here the transition function is simply that the next state is equal to the current state plus the value that we use to reach the state. And there is a second point that will prevent us to build node that won't lead to any solution. We'll see that just after. So we start from the root node, which we have 0. And we'll try all the possibility for the first layer. So for x1, so with 1, we obtain the state 1, and with 2, we obtain the state 2. We have finished with this layer, so we go to the next. and we will do the same operation for all the node of the next layer. So x2 can take the value 1, 2, 3, so we first try with 1, but we saw that we obtained 2, and as the second point says, we will not build this node because we can't satisfy the constraint from this node now with the remaining variables, so there is only x3 here. And if we had the max value, so 2, we can't reach 5, so we don't build this node, it's not necessary. With 2, we obtain the state 3, and with 3, we obtain the state 4. So now from 2, with 1, we obtain the state 3, and as it already exists for this layer, we bind it directly on the node. The same for 2 and the state 4, and with 3, we obtain the state 5. And for the last layer, we directly bind on the last node all the paths that are valid solution for a constraint. So with 3 and 1, it's not possible to satisfy the constraint, so we don't build it. But with 2, it is possible. From 4, with 1 and 2, it works, and from 5, it is the same. Well, so now we will see 3 different methods of construction for a product constraint. So the first one is the logarithmic method. So I remind you that the logarithm of a product is equal to the sum of the logarithm of its components. So what we do is simply we convert all the probability. I speak about probability, but technically it works also with all numbers, positive numbers. So we convert all the probabilities into their corresponding logarithm. And what we simply do is to transform the product constraint into a sum constraint, and so to do the construction that we saw just before. With this method, it is possible to perform a relaxation. We can keep only until the epsilon digit after the decimal separator of the logarithm. And doing this, that allows us to have a compromise between performance and accuracy, because the smaller is epsilon, the more equivalent states or merge we will have during the construction. And so the more equivalent state, the less computation, because we will have less node during the construction. So the second method is the exact product method, and it aims to be as accurate as possible, depending on the data we have. We decide to do it with integer. So we choose some value delta to transform each probability into its corresponding integer. So for example, with delta is equal to 4, we simply multiply it by 10 power delta and cut to avoid the next decimal after. And so for 0.98, we obtain 9,800. So the problem with this method is that it needs a data structure that can represent really big number if we want to always keep all the information. Because if we begin to multiply, for example, a number that are almost at 10 power 4, we quickly have an overflow with almost every language on the common structure that are used in this language. So yeah, we really need some kind of data structure. And it's the same if we want to keep all the precision with decimal number, because if there is a rounding, we don't want any rounding where we want to have the most accuracy as possible. And so the first method is, and last thing I forgot to say about this method is that for the construction is almost the same as the sum constraint. Instead of doing an addition when going to the next state, we simply do multiplication. And so the third method, the relaxed product method, that is the same as the exact product, except that we can relax this method. We do a relaxed product. That is to say that after each multiplication, as we are with integer, we will only keep the epsilon first digit that are supposed to be after the decimal separator. So we note it like that. And for example, with this computation, instead of having a huge number, we only keep the first 4 4 first digits, and we'll round them to the same. So before presenting you the results, I forgot to say that all the relaxed method were made in order to get a complete set of solution. That is to say that we are sure, even with the relaxation, that we get all the good solution, but there might be some wrong solution because of the relaxation. To compare this method, we decided to create some data. So we use data that represent 10 variables, each having 10 values in their domains. The value were randomly chosen between 0.95 and 1, and each resolution was made with a minimal threshold equal to 0.9. So first is here are the results for the exact product to have a base for the exact set of solution. And we can see that we can go up to 6 minutes of computation with 25 GB of memory consumption to represent a set that have more than 5 million solutions. So to compare with a relaxed method, we'll focus on this data. So remember this number of solutions. And here, first, before showing the performance, I will show the number of solutions that we get with relaxing method depending of epsilon. We also have here the lower bound, that it is the in the set that we get, it is the lowest probability of accident that we can find in the set. So it's here it represents the probability, the minimal probability that we get for the wrong solution. And an interesting thing to see is that we quickly decrease the number of wrong solutions from epsilon 1 and 4. But after that, there is almost no gain on the number of wrong solutions that we remove. And at epsilon 7, we are almost very relatively, it's almost near the exact of the set of exact solution, and for probability that is really near the threshold that we set. So we can see it more visually. So for epsilon 4, because before it is really high. And the time now, the evolution of the time depending of epsilon is really at the beginning it's really fast, but from epsilon 7 to 9 we see that it grow exponentially. So one first interesting thing to see is that we can obtain the exact set of solution with the logarithm at epsilon a, so at approximately with the logarithm method in 100 seconds. But another thing interesting to see is that we can have a really good compromise between the exactitude and the performance with epsilon 7, because it takes more or less 10 seconds to compute the MDD. And we get only a few number of wrong solution more for this precision. And so maybe we can use this information, this MDD at epsilon 7, to build more fastly the MDD of the exact solution, because if we want the exact solution, we see that the time really increase. And so this is the principle of the aims of the iterative precision refinement methods. So the principle of this method is the following. So let MDD epsilon be the MDD of the precision epsilon. We start building MDD1, and then we build iteratively MDDK from MDDK minus 1. Because the solutions that are computed in a relaxed MDD can be identified as search solution or uncertain solution. A search solution is a solution that no matter the precision will be always valid. For example, here with this computation, we don't need to note what are the digits after the 5 here and here. It will be always greater than 0.9 with precision greater than 2. And so uncertain solution are solutions that require a higher precision to determine if it is valid. So here with this computation, we need to know what are the digits after to know if this inequality is valid or not. And so the algorithm that use this principle use 3 different MDDs, each having a specific role. There is MDDS, that is the MDD that will accumulate the Searle solution during the iteration. MDDM, that is the MDD of the uncertain solution for a given precision epsilon. And MDDC, that is the MDD of the solution for epsilon plus 1 that we obtain directly from MDDM thanks to the on-the-fly intersection that Victor presented yesterday. So MDDC is fast to build because it don't build all those solutions for some precision from the scratch. It will only build a more precise solution from a previous MDDM. So here is the algorithm, and the main important part is the loop here. So at each step, we will build MDDC for a precision epsilon from a previous MDDM at precision epsilon -1. Then with this new solution more precise, we extract from MDDC all the uncertain solution. And with MDDC and MDM, we add to the MDD of all the Searle solution, the solutions that are not uncertain, so represented by this difference. And so now the result with this method. So here on the left are the time for the exact product method, and the logarithm with epsilon is equal to 9. And on the right, we have the time with the different relaxed method with IPR. And so we can see that it really decreases the time of computation. And it is the same with the memory. We really decrease the memory consumption with this kind of methods. And that's all about the results. So to conclude, we see that with a relaxation during the construction, it can lead to a good compromise between performance and accuracy, as we see with epsilon is equal to 7 for the example. But the IPR methods can greatly increase the performance to get the exact solution sets using this compromise. And we also see that the logarithm method that perform addition seems to be better than the other. So for future work, it will be interesting to see if it is possible to apply a kind of IPR method to other constraints with MDDs. So it's done now with product constraint and also with the sum constraint. But we already work a little about that, and it seems to be to work better with constraint that really cut the set of solution in both parts, like with an inequality, for example. Okay, thank you for your time.
Very much. Lots of time for questions. So I think you mentioned in the beginning that you want to use this to deal with uncertainty and things like that. So are the decision diagrams used as propagators essentially in those situations, or like as part of a bigger constraint model?
How we use this NDD? Yeah, technically, how can I say that? The work that we have done was motivated by the probabilities, but we don't try it we don't have try it in a real problem that involves uncertainty for the moment.
So now I think the question I had was whether if you don't want to compute the exact decision diagram, right, but just the relaxed one, could you add another constraint that just checks in the end, that doesn't perform any propagation, but just basically rules out the incorrect ones if it happens to?
So remove the correct ones, I don't think, but check if there is some wrong. Yes, you can do that easily, but check, remove the.
Yeah. Really just check at the end.
No, check, yes, it's possible to say that. We just, as the MDD is already built and reduced, I don't speak about that, but there is also a reduction after the construction of MDD to compress more. We can propagate some information, but this is how we saw that our set of solution get some solution that was at, yes, it was. So when we propagate the information, so we saw that there is some wrong solution that get this probability. So we are under a threshold, it's a false solution. But we know that there was this wrong solution.
Other questions?
Can you go to your pseudocode? So I was just wondering if you can comment on the time that the things in the loop are taking as you go through the iterations, because at the beginning, right, you're going to have different size MDDs, and I assume like MDD-M is kind of shrinking as you go through it, right? So intuitively, different steps are going to take different times at each iteration. I'm just wondering if you looked at the amount of time it took.
What time it takes every
for each of these steps within an iteration and how that evolves.
We don't do it for iteration, but we try to, for example, we don't begin to epsilon 1. We decide to begin later. For example, we saw with epsilon 7. There is no really it's complicated. There is no general rule about that. And
so I'm thinking, for example, MDD-S grows monotonically through these, right? And so the operations on it are going to get more expensive.
Yeah, I see what you say. I didn't really see what time it takes at each iteration, to be honest. So I don't know how it will be necessary. Yes, to see.
Yeah, maybe I can answer. So that because NPM is shrinking, the fact that it's shrinking so much, it takes very little time. The more you advance in the algorithm, at the end you have like 20 solutions to iterate over.
Yeah.
Usually it goes like this.
So this step here, the union is not the critical operation there.
No, it's no, I haven't the extraction.
Consider maintaining an interval for taking the outgoing arcs. This is a cumulative function in the sense that it's monotonely increasing function. You may have a lower bound and upper bound. This case, maybe it's a lower bound that proves some kind of property that you wanted to be the.
Instead of just cut for the relaxation, you mean?
Yes.
We don't try, but the problem is that when we go through the MDD, the interval will grow and grow, and just looking like that, it seems that it will be maybe less and less accurate in the both sense, but maybe it's something we can try, yes.
In fact, when we use it, we use a specific log function in which we control the error. Okay, so that this is implemented sometimes in such a way that you control the error according to I3D norm and give us the bound. So in fact, somewhere we manipulate it.
Yes.
We exactly have a lower bound which is precisely defined. And this is why we need to use, for example, we need to use specific log function which give you specifically the error of the product.
Tell us that we have to go to the coffee break. I'm not sure what that was.
It always happens when Jean-Charles is speaking.
Okay, so let's thank the speaker again.